Hast du im letzten Semester oder im letzten Semester hattest du ja erzählt, ja, vorstellen. Hast du bestimmt ein bisschen reduziert oder?
Ich überlege noch, ob es vielleicht noch so ein Fach oder so aus dem Fach ist. Ich glaube, es geht auch nochmal los.
Bei schönem Wetter, schick.
How's it going? Talk with you about the solar model, right? I mean, this is exactly where we stopped last week. So I don't know if you have any questions, things we should discuss. All good and clear. Okay, so then let me go back here. Maybe to have you all on the same page, right? So this is still my chapter 2, which is kind of still a call it introductory, but it's kind of one of the chapters that's supposed to lead us where we want to go, right? And like what I spent some time on last week was basically what I call this tour from old to modern macro, right? It's a bit like, what's the difference between, let's say, what you typically do in an undergraduate in ISLM compared to what we do in a modern macro model, right? So what I talked about for some time was the Lucas critique. Remember what I meant by Lucas critique. Yeah, exactly, right? So that's basically what Lucas said, right? So he said, come on, all these models, take an ISLM, right? I mean, Western could also take the ACD, right? Just take these models, these old style macro models, they are not micro-founded, right? And basically the point where he said that this is a problem is that if you base policy on these models, right? Could be monetary policy, could be fiscal policy, could be whatever, right? Labor market policies, investment policies, load policies, whatever you may think of, right? If you base policy on these models, you will basically consider people as stupid, right? You will take them as they will not adjust to these policies. right? They just keep behaving as they always did, because these models just don't have these micro foundations, right? So now basically going in circles, right? But they're not modeling the actual behavior of households, right? Different way of saying micro foundations, right? And if you actually want to have a model that is somewhat able, right, to make policy recommendations, implications, to think about this, you need a model which is micro-founded, right? And this is kind of this very crucial thing, right? So us macro people, this is kind of what we always talk about Lucas, and what we think that this is important, right? And this is kind of one thing that I wanted to get across last week, right? So why we believe that this is important, right? Okay, good. So then we basically started talking about the solar model, right? First disclaimer, the solar model is not micro-founded, but I will show you in the next set of slides how we can micro-found it, right? So that's basically kind of my first example of what micro-foundations then actually mean, right? To show you this. Okay, good. So we basically start with these two slides, right? So I gave you this very short tour of the solar and gave a bit of the hard work to Maria yesterday, right? So let me just give you a short reminder of what this model is, right? So you have basically here these four equations, right? That's the whole thing you need, right? So what you need is what I call here the accounting identity, which basically just tells you production, right? Output, GDP, whatever you want to call this, right? Equals consumption plus investment. And this is not surprising, right? That's the same as in an ISLM, right? What is a bit particular of the solar model is this particular idea of the production function, right? So this is a Kaptakis type of production function, and I actually already shortly talked about this. Maybe let me make some more points because they will become later even more important, right? So there's a lot of reasons why we choose such a production function, right? And I mean, one of the reasons that we will be using later is this here, right? This production function has constant returns to scale, is strictly increasing in k, and has this diminishing returns to k. What does that mean in words? So now I was describing mathematical properties, but what's that in terms of economics? What is constant returns to scale?
All input factors are multiplied by constant, and the output is also multiplied by the demand.
Yeah. In terms of economics, basically, in terms of these models, what that means is the size of your economy doesn't matter, right? So if I increase, as you just said, right, all inputs, in this case consumption and labor, are the same, right? So my economy growth, I have more worker, I have more capital. This will not change how you produce, right? Because you have constant returns to scale, right? Alternative example is increasing returns to scale, right? Increasing returns to scale would mean larger economies would have an advantage, right? Because there's increasing returns. The larger you are, the better you can produce, right? Something that you may see on the firm level, right? And we're basically imposing here that on the aggregate level, this is not happening. And there's a lot of reasons why we do this. One reason being that otherwise you couldn't basically not work with the solar model, right? Because then you have exactly this issue, right? Large economies have an advantage, right? So we're basically taking that out. That's constant returns to scale. What is this thing here? Strictly concave and increasing in k. So k is capital, right? So what does that mean for the capital input?
The more capital we are accumulating, the more output, but the next unit is not so efficient as the unit
right?
before.
And so the typical way how we represent that, and maybe let me give you that figure. If you plot this production function in k, how does that look like? Right, I'm increasing k here on the x-axis. So how does the output look like? Basically, what you're doing, I mean, it's essentially, right? It's concave, right? So that's exactly where it shows up, right? This is a concave production function, right? And this is doing exactly what you said, right? If you increase your capital input, you're using more and more capital. This increases your output. You're producing more, right? But what you're producing more, this is what's diminishing over time, right? So the additional output is getting smaller and smaller. And this is one of the very, like, you will see that, right? The whole solo boils down to this in the end, right? So capital is good, right? More capital is always good. It always increases your output. But there's this diminishing returns. And this basically means that there's a point where it stops, right? So that's the whole thing. Okay. This is our production question, right? Good. So this was this first two equations. So now the other two, which basically now we have to close the whole thing, right? We have to close the system. So the first thing that I gave you here is this capital accumulation, which is basically just an equation that describes how the capital stock evolves over time, right? And I hope this is kind of natural, right? The idea is that tomorrow's capital stock equals today's capital stock, right? Because that's the, and I said, this important property of capital, right? Capital, if you once you have it, you can keep using it also in the next period, right? This is what we call this idea of accumulator, right? Right? This is what makes capital particular, right? Once you buy a machine, you can use it from that period onward. It doesn't just disappear again, right? So this is exactly this idea, right? So today's capital stock is yesterday's capital stock. There's a bit of capital that disappears, right? Because maybe some of your machines just you cannot use them anymore. Maybe the technology is outdated. Maybe just it's like not working anymore. Whatever, right? You may come up with different stories. This is what we typically call depreciation, right? A certain share of your capital stock is not usable anymore in the next period. This is the share delta. Plus, you can increase your capital stock right by investing, right? This is design. Okay. So this is really like just, we call this a law of motion, right? You're just describing how the capital stock is evolving over time. So now comes the important thing. Actually, like all that we need for capital is already in the model, right? But what is missing is how do we now basically decide what share of production, what share of output goes to consumption and what share goes to investment, right? That's the thing that's missing. And what we do in the standard Solo model, which follows basically Solo, right? It's just to say, okay, we stay in the ISLM tradition and we just assume ad hoc behavioral functions, right? So I call this behavior here because this is a household choice, right? So I have a certain income. Out of that income, how much do I consume? How much do I save and invest? Right? So we're just assuming this, and what we're assuming here is the most simple thing you can do. We basically just say there's always this constant share S, which is the saving rate. Call this, right? You say like 20% of what my income I'm saving, like 10%, whatever, right? But that's just a very simple idea. Good. And I mean, as I already explained to you last week, when if you now combine this, you can describe the dynamic of your economy, right? And this is basically the new thing that I want you to see, right? This is the dynamic model, and I will talk about it based on this figure now in a second, what exactly that means. Right? Okay, so how can we think about the dynamics, right? I mean, for the dynamics, all that is kind of interesting here is the capital stock, right? Because the capital stock is the thing, as I just said, right, that remains, right, from one period to the next, right? So we should think about the capital stock, and for that, what I do is I just like take these equations 5 and 6, these two here, take that one here, insert that there, and then you basically end up directly with this equation. Now you can kind of do this for ourselves last week, where you can basically open many different boxes. First of all, this here describes the evolution of capital, right? I mean, basically, the interpretation is just the same as of equation 5, right? Which is like for investment, what I do is to use this behavioral rule, right? How does investment actually set? And what's important here, this rule, again, depends on K, right? Depends again on the capital stock, because the capital stock determines your production, and because of that, it also determines your saving and investment, and because of that it will determine the next various capital stock. And this is why this equation is important, right? This is an equation just in K, right? This is always depending on the capital stock. So to understand the solve, all you need is capital, right? So this is really a model of capital, right? All the other variables, I mean, they're still there, right? It's not like output doesn't matter here. Obviously, output is there, but it's also not that consumption doesn't matter. Consumption is there too, but to like understand the dynamics of the models, this is what you need. All the remainder you can basically do afterwards. Okay, so it's just an equation in K. So the first thing you could say is, okay, that's done, right? Just like think of K as an X. You have one equation in X. Okay, I can solve it, right? Why not? Is that an issue? Well, and there's a little issue here, right? This K here has two different indices, right? It's one indexed by T, and here it's indexed by T plus 1, right? So this equation tells you the capital stock tomorrow depends on yesterday's capital stock, right? Which is like mathematically, if you're like, I don't know, think about what you did in school when you were solving equations. I don't know, maybe you've seen it, most likely you've not seen it, right? This is not a dynamic equation. So what you need to do is you don't just have to find one x, one k, but you have to find a solution for k that holds an aggregate. And this is like what we do with difference equations. Right? So mathematically this is a very different thing, but we need this here because this is an economic model which has interesting dynamics. Alright. So how we work with these dynamics, I will show you exactly based on these figures on the next slide, right? So I'm not giving you the math yet. Actually, the math is coming later. We do that. The math is really away. Yeah, I just want to give you a bit of intuition. So what we typically do in these type of dynamic models is to ask, basically go and say, okay, I know these dynamics. It's a bit messy to deal with. It's not so easy to solve. So what do? We look for something that we can solve, right? Which is kind of doable, nice, and we kind of know how everything's behaving, right? And this is exactly what the steady state is doing, right? So what is the steady state? Definition here on the slide, but in words, what is the steady state of this model? What does it mean?
Our long-run output depending on the accumulated capital.
Yeah. So a long run in the sense of, in the steady state, your capital stock doesn't change anymore. And if your capital stock doesn't change anymore, also your output will not change anymore, right? So you're in a steady state, that's where the word comes from, right? Where your economy, you're saying that it has converged, right? It has moved to a point where there's basically no growth anymore, right? So you're in a constant situation. The capital stock stays constant, output will be constant, also consumption will be constant. So we have like kind of moved to a situation where the dynamics are gone, right? That's basically the whole point, right? So you said the dynamics is a bit messy. I'll like talk about how we work with that, but let's start with something where we can kind of like work more easily with that, and that's exactly the steady state because there's no dynamics anymore, right? So I mean, mathematically, basically what you just need to do is to impose this, right? So the only thing that we impose here is to say, okay, I'm looking for a steady state, and I define the steady state exactly like this, right? So I just say the steady state is then if the capital stock in T is equal to the capital stock in T plus 1, right? That was just basically, I hope that this is the mathematical representation of what I just gave you in words, right? Capital stock stays constant, right? Okay. And we typically call this K star, right? This will be my notation in the following, so if you have this star on the double, that basically means this is the steady state capital stock. All right. So now take this condition, impose this on this condition up here, right? And I mean, this is like doing that is super easy. You just get rid of these indices, right? And then call this K star. And then, like in this equation 7, you suddenly have something which you can solve very easy, right? I mean, this thing here in 7 is just one equation in K, right? This is one equation, one unknown, think of K as an X, right? Just solve it for X, which is what you have here. And then you basically already have a solution here in 7. I mean, there are different ways how you can write this, right? But this equation in 7 basically gives you this typical thing that you find in the Solow model. What does this equation tell us? Well, on the left-hand side, you have delta times K. Delta times K star, so that's steady-state capital stock, and that's the share of the steady-state capital stock that's depreciating, right? So you're in steady state, you have a certain capital stock, right? So you have a certain set of machines and houses and whatever in your economy, right? And out of that capital stock, a certain share is depreciating every period, right? So basically you just have to roll away because it's just outdated, right? For whatever reason. And now this equation tells you that this depreciated capital stock has to be equal, and this is now the right-hand side, to S times Fk star L. So what is that? Well, this here is, first of all, right, my production. This is what I'm producing in steady state. And this is the share of the production that we're saving and investing, right? So this is the new capital stock, right? So equation 7 is just telling you in words, the capital stock that you have to throw away every period has to be equal to the new capital stock investing, that you're generating. Because only then your capital stock will stay constant. That's just, I mean, in a way it's trivial, right? I mean, there's a certain share of your machines which is kind of like not working anymore, you have to replace that. Right? That's basically what this equation is telling you, right? If you want to keep your capital stack constant, you set up machines and there's a certain share which is not working, you have to make sure that you're replacing that. For steady state. Right?
And don't you just have to take the partial derivative then of K and solve it equally to delta?
Yeah, you're already one step further, so that's what you do if you're asking for this for the golden rule steady state. Right? So these derivatives you actually only need if you're asking, can we find a steady state where consumption is maximized? This is something that I'm not doing at all, right? So I'm just basically describing where this economy is going. I'm not talking about at all whether this is optimal in any sense, right? So what you have in mind is this golden rule thing, which you can also do, right? And has Maria done that already? Yeah, so that this is exactly what she did. For that, you actually don't need that. Right? This is just a thing. Okay, so now let me show you that here basically in my figures, right? Because I hope this here will give you the intuition of how we now solve this, right? So what I'm plotting is just what I just gave you in words, right? So here's the capital stock today, KT. This is the capital stock tomorrow, KT plus 1. So what I'm plotting first of all is a 45-degree line. So if you have the 45-degree line, this is just imposing that on this line, KT equals KT plus 1, right? So this is basically the steady state condition. Right? So on this line you have KT equals KT plus 1, right? And now I'm plotting this black line here. And this black line is nothing else than this equation up here. Right? So just this is KT plus 1 equals 1 minus delta KT SFK. And this is exactly it, right? This is SFK plus 1 minus delta KT. So if you want to have this equals KT plus 1 here, right? And then this is exactly the equation that you get on the other side. Right? Where does this shape here come from? Why does this black line have this shape?
Our production function and the defined concavity.
Exactly, right? So this is also why I just gave you that here, right? We're just inheriting that, right? I mean, just look at this equation. This equation has the production function, right? Because the production function also determines how much new capital will be there, right? Because new capital is just a certain share of production, right? So basically inherits here this shape of the production function. And I'm subtracting something here, but what I'm subtracting here does not change the shape of this function because this is just linear, right? It's just this depreciation rate. Just actually adding, right? Adding 1 minus delta, right? So this is just a linear thing. So this doesn't change the shape of this curve. And now basically comes the part where, I mean, here was just saying there is a steady state, right? And I mean, in the steady state, this holds. Using this figure, you can, in a way, prove that the steady state actually exists. You can think about when it exists, when it does not exist. And you can think about, does my economy actually go to the steady state, right? I mean, it could also happen that you have an economy with a steady state, but maybe it just doesn't matter, right? I mean, all these things can happen, right? And this is a bit kind of the beauty of the solar model, right? In the solar model, it's all very well defined, and that's kind of what I want to show you now, right? Okay, so maybe let me start from the steady state, right? So where's the steady state in this figure?
Right at the optimum.
Yeah, again, this is not the optimal, right? Maybe my notation from the start is not very good. Maybe I should change the notation. You're right. This is the steady state, right? So the steady state per se doesn't tell you anything about whether it's optimal or not, right? That was basically the other point that we had before, right? But this is where it is, right? So where these two lines intersect, right? So I mean, and the intersection of these two lines is just graphically basically imposing these two conditions, right? I mean, this black line, I just gave you that. This is this line. This is this equation, right? And now I'm also imposing this here by basically saying I'm on this 45-degree line, right? So the point I'm talking about is this one here, right? This is the steady state, and this is why I'm calling that K star here. And I see that my notation is not optimal. So I should use something different, but that's it. So this is really just a steady state, right? Where these two things interact, right? So I'm graphically basically imposing the same thing as we did like in equations on the slide before. Right? So now you can say one thing. I mean, first of all, this thing exists, right? This is already good, right? So we find this point graphically. Is this the only steady state?
There's also one at 0, 0.
Right. I mean, with the condition that I just gave you, right? I mean, where these two lines intersect, this thing here would be another steady state, right? And I mean, it is one, right? It's not like this thing doesn't exist, right? I mean, this here is an economy where we have zero capital, where you have zero production, where you will have zero consumption. But this is a steady state of this model, right? So this is how it happens. Okay. What we typically do is what you basically just say, so we condition on steady states which are interesting in the sense of you have actually a positive capital stock, right? So this is why this thing is always kind of treated a bit with like outside, right? But it's there, right? Okay, good. So yeah, this is the second steady state. So the other thing you can talk about now is, so in a way we've proven, let's say, using that word loosely now, right? There is a steady state. Now let's think about, do we actually go there to that steady state, right? As I just said, I mean, maybe you have steady states in your economy, but they just don't matter. And actually, that's another way of saying that this one will not matter, right? Whereas the other one does matter. So is it that we're actually going there? And here the solar model tells you a very clear story, right? And this is always why I like this figure, right? So consider a situation where we are off steady state, right? And I mean, this happens, right? I mean, you can have an economy which is currently here, call this K0, right? You have an economy which has a capital stock which is lower compared to the steady state, right? So what's happening in this economy? What do these two lines mean now?
On this point, the new accumulated capital is larger than the depreciations and the growing of the population.
Yeah, actually here population growth is out, so it's even simpler. It's really just the depreciation, right? So what this here means is here you're basically investing more than like one of your capital stock is disappearing, right? What it's depreciating, which means that here you're actually increasing the capital stock, right? So this is what this point tells you, right? So in equations, right, if I go back here, this is a point where SF K star L is larger than delta K. No, not star. Sorry, this is exactly. I should call this a 0 now, right? So this is an economy where the capital stock is relatively small, right? So a small economy, maybe a poor economy, right? That's the way to think about it, because also if you have a low capital stock, you're producing less, right? So lower capital stock, which also means that there's relatively less to depreciate, right? Because the capital stock is not that large. But at the same time, because you have less capital stock, if you have additional capital stock, you're investing, right? Think about the diminishing returns. If you are on the left-hand side somewhere here, right? The marginal output, right? The marginal production of your capital is relatively high. So investing more in capital is very good, right? And this is exactly what you see here, right? So here, this point is larger than, it's higher than that one. So you're increasing your capital stock, right? So like graphically, how I would interpret this is to say, this point here is above the 45-degree line, right? I mean, in a way you can just read it off, right? If you have K0, then in your next period, which would be K1, right, in my notation, K1 is larger than K0, right? So this economy is growing, right? So this is what makes this a growth model, right? This economy is growing. We are accumulating capital, and if you're accumulating capital, we're also accumulating output. We're accumulating GDP, right? That's basically what's happening, right? And this is what I'm basically also plotting here on the right-hand side, right? So here I'm plotting again the x-axis is exactly the same, but on the y-axis you have the change in the capital stock. As you can see here, if you start with a relatively low capital stock, again, let me call this K0, right? If you start here, then you see that the change in your capital stock here, right, K, I'm calling that K dot here, is larger than 0, so your capital stock is growing. Right? So what does that mean now for the next period? So what happens now in K1? Where am I going with my figure?
Further, what's K star?
Right? And that's what we call convergence, right? That is, right? I'm proving that graphically now, right? So we started here at K0. Now we have the positive change in capital. So we're adding capital, right? So my economy moves here. So we say K1, and he is here, right? I mean, just randomly making numbers up. It's to the right, right? That's what's important, right? So let's say K1 would now be here, right? So you're basically moving here. Now you can do the same thing again, right? Also in your K1, your capital stock is still below. Your capital stock is still below the steady state. So you still have the situation that there's relatively less depreciation compared to the new output out of your capital, right? This is exactly what this equation tells you. So the capital stock is still increasing, right? This economy keeps growing, right? We're still above here. So K2 is still larger than K1, right? So this here will now be my K2, right? And I mean, now you can continue, right? So now K3 would be, again, if I would plot K2 here, and then K3 would again be larger, right? So we would just be moving here, here, and here, right? How long until we hit this point? because at that point, then the depreciation is exactly equal to the capital stock, and that's where this is stopping. Right? This is what we call the steady state, and this is what we call convergence to the steady state. Right? And I mean, in a way, you can already see why we converge. Oh, I mean, this is our production function, right? This is the whole magic of this decreasing returns, right? If this would not be there, this would not happen, right? So this is why this whole idea about this capital is accumulated over time, and you have this decreasing returns. This is really the core of this model. But also economically, right? And I mean, this is why, I mean, the Solo model has many issues, right? And we'll talk about many of them. But the Solo model has also very interesting and clear predictions, and I would say this is one, right? So this tells you an economy which is below the steady state capital stock, right? That economy grows. And it grows until a certain point, and then it stops growing, right? So this is not a model about infinite growth, right? There is a steady state where we're stopping, right? And this is very clear. This is just the result of this diminishing returns in capital, right? So it's not like this model here gives you, this, whatever people think of when you talk about infinitely growing economies. This is just not the idea of the Solo model, right? And the reason is exactly this, diminishing returns, right? So basically it tells you very clearly, just out of the capital stock, out of saving, out of investment, you can grow, right? But only up to a certain point. Right? And I think this is a very important message actually out of this model. Okay. All right. I'm also showing you this figure because what I do here now, and I mean maybe just to say this one, because we will be doing this again in the neoclassical growth model. So understanding this figure and what I'm doing here is actually important. So what I do here is basically to show you a figure, right? And I mean that figure is very stripped down, right? It just says you just have these two dimensions, kt plus 1. But still in a way, I'm showing you dynamics in this figure, right? So the point that I just made was to go like, we go from K0, right? This would be, I don't know, 2021 to 2022, 23, 24. We think about how this economy is evolving over time. This is exactly what we do here, right? And this is what we will continue doing in all of our models that will come, right? We will always be thinking about dynamics, and this model is already doing this, right? And this is exactly where I wanted to start there, because that's what I want you to see. Right?
Is there sort of any way that the country can overshoot the steady state and basically get to the right and then converge back?
Yeah, very good. In principle, yes, right? I mean, the question is always how you think about deviations from the steady state, right? I mean, one story we typically tell here is, I don't know, think about Germany after World War II, right? Lots of the capital stock is destroyed, so we are growing back to the steady state, and this is typically how people also explain this high growth period after World War II, right? But now you could also have a situation where you're sitting on the right. I mean, why could that happen? I don't know, but maybe, say, you have an economy where for some reason, let's say the saving rate depreciates, goes down, right? So if suddenly, for whatever reason, because people are now very afraid, or people become very uncertain of what's going to happen in the future, and they suddenly save their savings, change their saving rates. Let's say saving is not worth it anymore, I'm not doing that. So if they change that, right? So you would need changes in this fundamental parameters, right? Could be the saving rate, could be depreciation. The more natural thing would also be to say, if you extend the model, for example, towards population growth, right? This is something that I'm all about having here, right? But you could have situations like that, right? So basically your capital stock would be too high, right? And then you can make exactly the same argument, right? I mean, you can say, let's say now we start here. So let me call this, I don't know, K0, A. Nice notation, but you know what I mean, right? So this is just another economy now, right? Where you have exactly that situation. So what's happening in that economy?
You basically depreciate then you gain.
Yeah.
So you have
Yeah. So there could be a situation where you say, for some reason, people suddenly don't save anymore, right? So this is why you have a lot of capital. Out of that, a lot depreciates. If people don't save anymore, you have too little investment, and you cannot replace your capital stock anymore, right? And this is then why over time the capital stock would decrease. So if you were here, you would now be here, right? You would be to the right of the capital stock, of the steady state capital stock. So this here would be K0A, right? You would have a negative change in the capital stock, so it would depreciate. So it would go down. Right? So that economy would be shrinking. Right? And we just had population growth, right? Maybe demographics will give you this. Right? I mean, this is not out of the, this can happen. Okay. Good. Further questions on this? So I can spend hours talking on this because I actually do believe you can really, like, this is just for figure, right? You can basically, you can really take a lot from that, right? So first it kind of, again, I'm using the word proof now in a bit rough way, right? It basically proves you that your economies, and this is exactly what we just said, right? Either if you come from the left or if you come from the right, you will always move to this steady state here, right? To this KSR. And this is kind of a way of, I mean, you can also show it formally if you want, but basically the only thing that you need for that is this diminishing returns, right? If you have that, then this is going to happen. And you will never move here, right? This is also a message, right? I mean, I just said this steady state exists, right? So it's a formal steady state of the model, but like even if you started here, right? Very close to the 0, 0 steady state, your economy would move here, right? So this is just another message, right? This is why this thing here is not important, right? Good. Yeah, and I also always believe that it also actually tells us kind of an interesting story, right? Because it really tells you this. Our economies grow out of capital, right? They grow out of saving and investment, right? But always just for a certain point, until a certain point in time, right? So I mean, the typical argument that I'm given in undergraduate is to say, I mean, this model has this very clear message, right? If you, like, as a policymaker, right, you tell your, I don't know, your population, we have to save more, right, because we want to grow. This works, maybe, but only in the short run, right? And this is exactly one thing that the solar model tells us, right? So capital is good, right, for production and everything, but there's a limit, and that's a very important thing. Hello. Yeah, I mean, if you want, you can actually start immediately, if that's okay. Yeah. I actually have a short surprise, so I have to like kind of explain that first. So I mean, maybe some of you have heard that before. We have here luckily our Hochschulsport, right? And what these people offer to us, and this is what I actually always like doing, is that we have a little break in the middle of a lecture. So, yeah, so Nina will basically give you some exercise. And you're very welcome to join. So it's really the idea is like 3, 4, 5 minutes, and then we come.
Jetzt haben wir auf Arbeit auch. Ja?
Ja, genau. Wir brauchen es dann lieber gezwungen zu machen. Ich würde einladen, man kann sich sagen, ja, das ist nicht. Meine Idee war auch einfach das Fenster aufmachen, dann kann man auch schon laufen. Und hinterher wird es ja also wenn nicht, dann müssen wir die Tour mit live sein. Genau. Dann schaffen wir auch gleich nicht, aber die Arme überkommen und dann ziehen wir uns die Wechsel nach dem
Stabilen Stämmchen weiter.
Links, rechts und einmal die Arme absenken. Dann nehmen wir einmal die Arme nach vorne und wir schieben einmal den Arm aus dem Schultergelenk raus und wieder in das Schultergelenk zurück. Genau, wir schieben raus und ziehen wieder rein. Vor, zurück, vor, zurück, vor, zurück, vor, zurück und lassen die Arme noch mal aushängen. Dann strengen wir uns einmal ganz kurz an. ich hätte so klein geschrieben. Ich habe extra eine neue Aufgabe heute für Sie alle mitgenommen. Okay, andere Position. So, Vorhalte. Genau. Und zwar einmal vor dem Gesicht schließen und dann einmal öffnen nach hinten. Genau. Und wir schließen nochmal. Okay, nach hinten, öffnen. Aufmachen, genau. Schließen. Öffnen. Zweimal noch. Einmal noch und ausschütteln. Sehr gut. Nächste Punkt noch mit drauf. Und zwar schieben wir mal den Kopf jetzt aus dem Hals nach vorne und wieder zurück. Genau. Die kleine Schildkröte aus dem Panzer, genau. Also euch sieht niemand, ja. Ihr seht mich, ich sehe auch einmal aus. Okay. Wir gehen vor, zurück und dann merkt ihr auch das Knirsch und Knirsch. Genau, das bewegen wir halt nicht so wenig. Wir gehen vor, zurück. Und zweimal noch. Sehr schön. Und noch einmal auslockern. Und dann einmal auf ein Bein stellen. Wir nehmen einen Fuß auf die Seite stellen, das ist ein bisschen mehr Platz. Und dann einmal den Fuß zu Po ziehen. Kurz halten. Und dann schieben wir mal das Becken ein bisschen nach vorne. Wir kippen das einfach. Dann merken wir schon, oh, dann wird die Dehnung intensiver. Und halten da noch ein bisschen gegen. Dann sind wir hier auf dem Hüftbeuger. Der verkürzt gerne, wenn wir lange sitzen. Und wenn ihr merkt, das lasst da, einfach gerne das Becken noch ein bisschen vor. Nochmal intensivieren. Und dann einmal die Seite wechseln. Erst einmal kurz halten. Und wenn man sich mal gewöhnt hat, dann Becken vor und intensiv dehnen. Sehr schön. Und dann nochmal locker lassen. Dann tun wir nochmal einmal volle Übung vor dem Körper. Wir verhakeln die Finger miteinander, immer ein Daumen ist oben. Und dann ziehen wir mal ganz kräftig gegeneinander und versuchen auch die Schulterblätter voneinander wegzuziehen, um dann ganz bewusst locker zu lassen. Genau, und nochmal, alles nochmal einruckeln und dann, wir ziehen auseinander, wir lösen die Schulterblätter auch voneinander, halten, 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 locker lassen. Einmal noch, wir halten und ziehen auseinander und lösen. Und dann greifen wir nochmal einmal um und machen das nochmal in der anderen Position. Also, ziehen, kräftig ziehen, es darf ruhig ein bisschen anstrengend sein und Schulterblätter lösen und locker. Schulter unten lassen, wir ziehen die nicht hoch, ja, wir lassen die unten, wir ziehen sie voneinander weg. Genau, halten, 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 locker lassen und einmal noch auseinander ziehen, Schulter voneinander wegziehen und locker lassen. Sehr schön, letzte Übung, wir positionieren einmal unser Kinn über den Schlüsselbein, also so auf dem halben Weg zwischen Brust und Schulter, legen die Hand auf den Nacken und dann dehnen wir das Kinn auf das Schlüsselbein, also dehnen den Nacken, indem wir das Kinn runterziehen. Und dann merkt ihr bestimmt schon, wir sind jetzt hier auch am Hals auf der Außenseite. Da könnt ihr mit dem Kinn so ein bisschen spielen, sucht mal eine Position, wo ihr merkt, oh ja, da ist gut. Da ist gut. Und dann bleiben wir da. Und dann nehmen wir das Kinn an, wandern rüber auf die andere Seite, auf das Schlüsselbein. Dann wieder auf den Hinterkopf, sanft von unten ziehen. Und eine gute Position suchen, wo hier am Hals auch eine Dehnungsspur ist. Locker lassen, die Schultern nochmal ausschütten und dann sind wir auch schon fertig. Und bei euch geht's weiter und wir sehen uns nächste Woche wieder. Dankeschön.
So, I hope everybody's awake again. I just started that last year. And I'm actually like, I really like that this also stops me talking for my courses also good, right? And I actually always have the question that it's also nice for you, right? Because you have another way. And I mean, right, it's even better that way, right? If you don't like this, right? If you don't want to do like these exercises, that's all good. And you can also like go out for 2 minutes, just make sure that you're like coming back in time there, right? It's really like just that we have a short break for everybody like to also get some air. And it's always a very good point to like also ask me afterwards, do you have questions? Because I mean, maybe you've thought about this, I don't know, maybe you've thought about other stuff, but if you have thought about it, are there?
Isn't this model a bit outmoded? I mean, today it's...
It's not microphone, yes.
No, I mean because it's possible to invest without savings, or isn't this the case?
That's very good. Yeah. yes or no. I mean, so this model, I mean, you can basically, so what you can do here is you can also eat your capital stock, right? So it's not like you can even dissave here, right? So this is also like negative. So this is all here, right? So this is not a model about financial markets, right? I think this is what you have in mind, right? So this is not a model about finance and how we actually do this, right? Then you get additional mechanisms too. This is also not a model about open economies, right? I mean, obviously, in the real world, investment can also come from other countries, right? Which is also not happening here, right? So the way, yes, but I also, to me, right, it doesn't change these mechanisms, right? I mean, also if you have investment, let's say coming from somewhere else, right? And I mean, yes, financial markets are important for investment, right? I mean, you can add all this, right? But to me, it wouldn't change, like, the main insight from the solar, right? To me, really is this point. We can grow out of capital, but it stops at some point. All of that will go through, right? So that's always, maybe that's a very good example, actually, right? Of what I mean by this model is wrong, right? There's many things that we're abstracting from, but it focuses on particular mechanisms, right? And I mean, the solar model really focuses on this capital accumulation. This is all it does, right? But I still think it tells you the story about this, right? And yeah, you can extend this along many of the dimensions that you mentioned. Finance clearly is one, right? I mean, maybe I shouldn't go too broadly, right? But I think we actually go there at some point, right? So one big implication of the solar model is, right, that let's say you were to use this model and think about this, I don't know, maybe the US is here, right? This is where the US is already very close at steady state. This is why they're rich, whatever. Maybe they're actually even at steady state, you name it, right? Whereas other countries, I don't know, maybe take China or take a country in Africa. I mean, we talked about this, right? Sub-Saharan Africa. Could we think about these countries being more here, right? And I mean, obviously, this model would then predict, if you think about it that way, that these economies would be growing like crazy, right? So the solar model will tell you that Africa should be growing, right? A lot. But I mean, I showed you that this is not what's happening. Data, right? I mean, if you ask me, I think financial markets are a huge reason why, right? But yeah, we will actually get back there, right? Good. And it's also not microphone. Another reason why. Yeah. Yeah.
I have a question about the slide prior. I understood the point. No. Wait, with the
Figure, yeah.
the figure. My question was about the figure on the right-hand side, because you said that this also shows us that we always choose the steady state, but I didn't quite get why this has a different slope.
You mean this figure, why this line here has a different slope? Yeah, I mean, yeah, that's a very good point. Actually, I haven't talked about that much. It's just, that also goes back to your question about like the optimal, where should we actually go, right? So I mean, what's happening on this slide, on this line here is basically, so if you're an economy here, I don't know, let's call this point A, right? You have a very little capital, right? So then the slope of this change here in the capital stock will be relatively high, which basically comes out of this here, right? If your capital stock is very small and you invest more, you will actually get much more output out of it due to the production function, right? But if your capital stock grows, then this diminishes, right? So this is why the shape here, this is actually disappearing, right? And then there's a certain point from which one onward, actually, like this depreciation kind of starts a bit overtaking, right? Because if your capital stock has a certain size, that right, you need to invest more and more to actually replace that. And this kind of already means that there will be a point, which is actually now here, right, from which onward, you're still increasing your capital stock, right? But it's already like the growth rate in the capital stock is already falling, right? So which is basically hiding or going towards at some point we will converge. Right. Which here on the left, this would basically be the point here, right? Where at some point, basically this line is overtaking there.
The dot above the K indicates there's a
so this is really just a notational thing,
but
actually.
it's
Like-
a derivative with respect to time, right?
Yeah, I mean, here I'm actually abusing notation a lot. So I think I said that last week, right? So like, if you open, let's say you open the Archibald textbook. Archibald is all of this, but you just let in continuous time. And in continuous time, you typically have exactly this notation, right? Where you say k dot is the derivative with respect to time, right? Here I'm defining k dot as just like this discrete change, right? Kt plus 1 minus minus kt, right? So here it's not the derivative, it's the difference, right? Which is the reason me being in discrete time, very often you see then continuous time, and then it would be the derivative. Right?
But in general, the right-hand side graph is just the change in
This is just the change.
the set and the left.
Yeah, that's the idea. I mean, the reason being, right, the idea is what you do in continuous time, right? You're basically in continuous time, you make this interval here between t and t plus 1 very, very small, right? So you make time continuous, right? That's this idea, right? Here I'm thinking in, call it years or quarters or whatever, right? And in continuous time, you're going basically to days, weeks, days, seconds, right? And at some point, just nothing anymore. And then this thing becomes a derivative. And this is actually like, mathematically, continuous time is always very nice, right? Because then you can work with derivatives. That's exactly the reason why we do this. But as I said, I'm not doing that here because I think it's actually much easier to have it. Okay, so let me now throw this at you. Basically, I already gave you all of this, what I have on this slide, but now I just use some more words for that, and then you know later what people mean by that if they talk about this, right? So, I mean, it basically said, like here I'm proving we have a unique steady state that we're converging to, right? And you can like formally show what kind of things you need for this, right? And I mean, in a way, it's always good to know, right? I mean, this is also a bit about what assumptions are crucial here. And this is basically what this slide is telling you, right? What assumptions are crucial for what I'm doing here? So first of all, this production function is crucial, right? So what you will need a continuous production function which is differentiable, has positive and diminishing marginal products, and constant returns to scale. I mean, this is kind of how I started this whole thing, right? Not surprisingly, our Count Douglas does all of this, right? But I mean, obviously you could have other production functions in mind, but then this whole story wouldn't work anymore, right? And actually, one is not enough. You also need two. And two is what we call our Inada conditions. So Inada, I mean, is basically a person, right, who showed this, right? You need these two additional things for this to work, right? So, I mean, this looks a bit ugly because it's about limits, basically, right? So what does this tell you? So this here tells you that you need, first of all, that in the limit of the capital stock going to 0, right? This is how to interpret this here, right? So basically, if you go here, right? If you think about the capital stock approaching 0, this is what this term here tells you. Then the marginal product of your production function with respect to capital must approach infinity. Right, which is basically just this, if you have an economy with very little capital approaching 0, right? Basically approaching the situation where you're going towards this 0 point here, right? Then you need a derivative here of 0, right? So you need this very steep slope, right? So here you need this to be infinity. Right? This is the first thing. So basically about, if you want, so about the beginning of our production function, right? The second condition is about the end of the production function. If you now increase k towards infinity, so what this thing tells you is then that the marginal product of capital has to approach zero. Again, our calculus is nicely doing this, right? If you follow this here, we're increasing k towards infinity if you go always to the right, right? So you're like really increasing k here. And then this slope here, at some point, is going to approach zero, right? Become a flat line. And that's again these diminishing returns, right? But this has to happen. And this is just what the second thing here tells you. Okay. Yeah, I see it is again. And then maybe just one way to make that more intuitive is to let me show you some situations where this is not working, right? So what could this be? What could this mean, right? So I'm basically showing you 3 different figures here, right? Which is again, this is always the figure I gave you before, but slightly different, right? So let's think about this, right? I don't know, let's think about panel A. What's going on in panel A? Do we have a steady state? Or do we have one steady state? Or do we have 0? Or do we maybe even have multiple steady states? What's happening in panel A?
We have the first 0, 0 steady state, but no steady state after that, because I guess we don't fulfill the first in other condition.
Exactly, right? So maybe let me just, for illustration, right? This is this figure. Now let me go to, this is my original one, right? So what's the difference? I mean, this point here is the same, right? This is the 0, let's say. But then basically what's now missing is that we are, like the increase at the origin is large enough to bring this line here above the 45-degree line, such that there's an additional intersection, right? Here, this increase here at the origin, I mean, it is increasing, right? It's not like this marginal product is not there, right? I mean, this is all happening, diminishing marginal products, whatever, right? This is all there. It's just not enough, right? And this is basically an example of this thing here not working, right? So the increase here in the production function here, it has to be something like this, right? So that you actually do get here this nice steady state, right? But here it's just not enough, right? So this is exactly as you said, right? This first united condition not doing what it's supposed to do, right? And I mean, basically that might be, like in economic terms, right, the gains to capital, to investing in capital are not large enough, right? And this is basically why this economy here is never coming out of this 0, 0 steady state, right? I mean, if you ever heard of this poverty trap idea, right? So like sometimes people actually also, I mean, if you think about it, I showed you this, right? That basically for a long time we didn't have any growth, right? And also like if you think about, like say, sub-Saharan Africa, right? Sometimes people argue that they are still in the situation, right? These countries are just not growing. And maybe this is a way to think about this, right? So an economy here, where you have such a situation, they are basically stuck in this poverty trap, right? And again, right, the solar model has many issues, right? I'm not selling you the solar model as this is the greatest model ever, right? But it can actually tell you a bit about this too, right? I can help you think about this, right? Basically, the gains to capital are just not large enough, right? And I would totally buy that financial markets play a role in this. That's not to say, right? But here you see this. Okay. What's going on in panel B? Sorry, go ahead.
Does this mean that the appreciation in capital is bigger than the New York?
Yeah, in a way that's true too. Yeah, exactly, right? So what's happened here in the original point is that investing in capital, what you're depreciating is always large, exactly, right? And then you're never really getting out there. Yeah.
What normally happens after the steady state.
Yeah, exactly, yeah.
Yeah, in the panel B, there's infinite steady states, or no, there's none, because it's ever increasing, so you never stop them to grow.
Exactly, right? So here, so there's one steady state again, the 0, 0, 1, right? But that's not maybe not the most interesting. Maybe it's actually interesting, but whatever, right? It just happens.
assume that in that specific place we would have growth larger than 0?
Yeah, very good. So that's basically like depending a bit on this definition of this limit, right? So this limit term always tells you you're approaching a 0, but you're not exactly at 0, right? If you're exactly at 0, then you're not getting out, right?
Yeah.
Then you stay in 0, 0 because once your capital stock is 0, you're producing nothing, right? There's no chance to get out.
Is this really occur in real life? I mean, you can always sell something, right? So.
Every model is wrong. And I don't think this occurs in real life, right? But I mean, it's basically a way to think about this, right? I mean, as I said, you could, if you want, right? And again, right? I think there's also different ways to think about these poverty traps, right? But this could be one way to think about this, right? And I mean, obviously, also in these countries, the capital stock is not 0, right? It's just that it's just not large enough, right? It's exact 0, though. But it's right. It's supposed to tell you a mechanism, right? And could explain this. Exactly. But then what's happening is what you said, right? So there's no intersection. So there's no second steady state here. There's no interesting steady state, basically. Why is that? So what conditions here is the problem? Exactly, right? Because I mean, this thing here is just going and going, right? We're not really having diminishing returns here, right? So this thing here is not working, right? So this here always keeps increasing. This is not approaching 0, and I mean, it's also like how it's plotted, these diminishing returns are just not moving, right? I mean, then you basically see what happens. Okay, what's going on in C?
C, we have multiple steady states, and I guess all steady states towards which we are converging depends on our and down capital.
Right? So there's these 3 steady states here. We'll continue because it's got even more, right? So, I mean, yeah, as you said, right, depending on where you would be starting, let's say you would start here, then you would converge here. If you were to start here, then you would converge there, right? So that really depends on where you are. I mean, you could now try to interpret this economically, but maybe that would even make sense. But in terms of these assumptions, well, what's the problem here with this panel C?
There's a production function that is strictly concave.
Yeah, exactly, right? I mean, what's happening here is you basically have this going up and down and up and down. Right? It's just, that's not what I gave you here, right? It's just like, I'm not saying that I believe in a production function like this. I don't know, maybe you can make a case that this actually happens, right? But I'm just like trying to tell you why we always have this particular form, right? And what happens if you're not having that. Okay. I'm basically not wrapping up, right? So this is kind of what I wanted to show you about this whole model. Again, right, I do believe that this is important, and it will be showing up again, right? So you will see figures like this here again. So it's very important that you maybe invest some time and really understanding this. I think this is helpful. And I mean, this is stuff which is actually coming back later. But just to say it once for completeness, right? So the solo model is a competitive general equilibrium model, right? I talked about DSGEs earlier, right? In a way, this is one. It's not stochastic, there's no stochastic, it's a DGE, right? But this is exactly what's happening here, right? So what does that mean? So here we have, first of all, that all markets clear, supply equals demand. This is here in that model, it's actually very simple because there's only the product market, right, where supply equals demand. And there's the capital market, where supply equals demand. And if you want, there's a labor market. Even in my model, I shut down the labor market, I was just constant, right? But always supply equals demand, right? So we are always in a competitive equilibrium. So all markets clear. But it is like this model is perfectly closed, right? And this is kind of what will make up our macro models that I will show you later too, right? So what's happening here, I mean, labor and capital are owned by households, they're rented to firms, and this will mean that in this model you have a very nice and clean definition of the prices of these factors. I haven't talked about this in my presentation of the earlier model, right? But you do define an interest rate in here, an interest rate, you also define a wage here, right? This is all there, right? Because it comes out of the market clearing, basically, right? So there's well-defined prices. And what's basically happening if you were to write down the full model, right, that the firm is actually maximizing profits, and this is where these prices will fall out, right? Which basically always means, and I mean, just basically, we'll show this later too, but I bet you've seen that before if you have some econ background, right? So what is happening in this model is that the wage equals the marginal product of labor, and that the interest rate is equal to the marginal product of capital, right? Again, we get back there. I just want to make this point now that this model is, in that sense, a complete model, right? It's all there. Yeah, the price of the final good. We can just normalize that. What is right as well? That. So this is kind of this, again, using micro stuff, right? But I'm just using that, right? So Waller's law always tells you if you have n markets, right? And if you have the prices determined on n minus 1 markets, the last price is then determined 2. This is why we're normalizing that. And I mean, here we have, as I said, the goods market, the capital market, the labor market. The wage is determined, the real interest rate is determined, so then the goods price, right, of the goods market is basically determined too. That's Waller's law, and this is what we basically say is 1/7 normalized. But this is all happening here, right? I mean, even though I just gave you these 4 equations, there's actually a lot going on, but I will also show you that later. Once you do the full neoclassical world model, we do that step by step. Okay, so yeah, so this is now a bit of a, what can you now do with this model, right? So Solo really focuses on this idea, right? We see growth due to this capital adjustment of steady state, right? That's this figure I just talked about a long time, right? Obviously, it's not the end of the story, right? So, I mean, maybe you've heard about exogenous versus endogenous growth model. This is an exogenous growth model, right? Because what happens in this model is that in steady state, there's no growth anymore, right? That was our definition of a steady state, right? In steady state, we said capital is fixed, output is fixed. But like in the first week, I gave you these Caldo facts, right? And one of these Caldo facts was that our industrialized economies are actually growing on average. So that's contradicting each other, right? So apparently the Solo model that I just gave you is not fitting this Caldo fact, right? And the reason is that in steady state there's no growth left, right? But in the data we do see growth, right? And I mean there's different ways how we can add this to the model. I would say the most interesting one is to think about endogenous growth, which would basically mean you're modeling productivity, right? Your production function and productivity, we sometimes call that total factor productivity, TFP. More carefully, for example, thinking about research and development and human capital, right? We'll actually get there later, like my last chapter, which we will do in January at some point, will be talking about endogenous growth models, right? So basically what I do there is to take a version of the Solo and add this. Right? Okay. Maybe some of you have seen this growth accounting. I will also show you that at some point, because that's one of these very nice applications that you can do with the Solo. But actually, and this is why the Solo model is one of these things that has become so important, is you can also use it for business cycles. You cannot, I mean, it is a growth model, right? That's what we call it. But you can use it for business cycles simply by the only thing that you need to do is you basically need in your production function, right? So typically we think about a production function equals f of, this is what I said, right, k and l. And now say, use a Cobb-Douglas, I don't know, k to the alpha times l times 1 minus alpha. So what I'm talking about now is this a, right? So this is what we call productivity, TFP, whatever you want, right? So I'm talking about this guy now, right? The Solo model per se doesn't talk about it, it's just like given, right? We basically want to make it interesting. We will talk about this, right? I mean, obviously, many people would say productivity is important, right? And I would say that too, right? So what business cycles models do is basically take this as it is and make this productivity go up and down, right? So maybe we have situations when productivity is high, we have situations when productivity is low, and then you can actually just take the solo model and think about the adjustment, what's happening, right? And it can actually tell you something about this. Right, you would have, for example, an output fluctuating, right? Which is exactly business cycles, right? Recessions, expansions, whatever. Good. Oh wait. Oh, good. All right. For some reason this has died now. Do you have questions? That's always a good. What is this? Any questions? Questions?
What causes A to have a stochastic nature?
We'll discuss that for a long time, so we get there. I mean, you could think about surprise innovation, right? So there's, I don't know, AI, right? So there's some lady, ChatGPT released, right? Firms use it, so that's something you could think about, right? But we get back there. It's one of the big questions we have to answer, exactly. Okay. I should really be careful pressing buttons before everything. Okay. So, but before I do all this, right? So before we will like move towards endogenous growth or thinking about business cycles, what I want to do first is go back to my point about the micro foundations. Right? So what I will do now is basically relax this assumption of this exogenous saving rate, right? Which was basically just then putting in his ass into the model. And make that micro-founded. Right? And what we will need to do for this is to really think about consumers. Right? We will really need to think about households, how they consume, how they save. Right? And I mean, to me, this kind of does two things, right? First of all, I will basically show you with that the neoclassical growth model, because if you take the solo model and add this, you have the neoclassical growth model. The second reason why I show you this is to show you an example of what I mean by micro foundations, right, and how we do this, right? Good. Because maybe just to give you this example again, right, in the solo model, what happens, this parameter S, right, this saving rate, is always fixed, right? It is never changed, right? Depending on whether you're growing or shrinking or whether you're very far off steady state or whatever, right? This thing is just constant, right? And I mean, this is basically what we want to get out, right? But we want to explain where this S comes from, right? And what it's actually doing. And I mean, in a way, that's also, we say, we endogenizing that. Good. So that's this chapter 2, right? So my idea was to basically first explain why we need these micro foundations. I kind of was talking for some time now about the solo model, right? Why I think it's important. And now I want to put the micro foundations in the solo. Good. I'm not daring to press full screen again, but maybe because of them likely to freeze again, right? Okay. So let me go there. So let me just start a bit. I mean, we will not do the full thing here, but I mean, given that I have 10 10 more minutes. Right. So that's now the purpose of my chapter 3. Right? Talk about this consumption and saving decision. Right? So this chapter will now basically move away from capital and everything, right? I mean, this will show up again, but just once we make it back, go towards the GE, the general equilibrium. Right now, I really want to focus on households. Okay, yeah, that's basically what we do. I mean, kind of in terms of methods, what you will need for this now. This is now, what I will do is I will make also the household problem dynamic. So what I will, like in terms of the method, what you will have to learn is intertemporal optimization. Right? So like basically, I bet you've seen a Lagrange, right? You will see a Lagrange again. You will see a Lagrange where you're not just thinking about one period, you're thinking about, in the end, infinitely many periods, and we are optimizing over time. Right? So it's basically do a Lagrange, but also think about the time dimension. Right? So that's kind of the method thing that you will see. Okay. So let me try to walk you a bit towards this, right? This is basically what's set on this slide, right? Is optimizing over time. And what we're doing is endogenizing this consumption state. Exactly. Again, basically you can open every textbook. I put here the NIPELs on this slide because it has a very, so the NIPEL is actually a super narrow textbook. It looks like this, right? So if you like it very concise and to the point, that's definitely what it does, right? And I found like this part in that textbook, I found that super nice, but I mean, Hachimoto is doing that too, right? It's not there, right? And the Roma is doing that too, obviously, right? Okay. That's basically what I already said, right? Just maybe to say that once more, what does endogenous mean here in this context, right? In the solo, we have this parameter S, right? And this saving rate is just constant, it's always the same. Once I have walked you through these micro foundations, we will not have an S anymore, but we will have a consumption saving decision, right? Which always implies an S, obviously, right? It will imply a certain saving rate. But this share that is saved will then be endogenous in the sense that it will depend on your current level of production, your current level of capital, your current level of whatever you want, wages, interest, right? So in that sense, it will be endogenous, right? So in the solo model, you can increase the interest rate, but people don't save more, which is maybe a big question, right? And this is exactly what we will change, right? Okay, good. And yeah, why is this so important? Basically, you already said this, right? Combining solo with this endogenous saving gives you what I call here the core of a modern macro model, and will be basically already the neoclassical model. Right? And I mean, just to show you where I'm going, right? The neoclassical growth model is exactly then what we were using in chapter 4, right? So chapter 4 is basically just take chapter 2, combine it with 3, and then you have the model out of 4, right? So again, this is why I think what we do now is important, right? Because it's basically showing up again and again, right? Again, right, also 5 is business cycles in the neoclassical growth model. Also in 5 you will need this. You kind of also need that here, and in the endogenous growth you will need it anyhow, right? So this is like really the foundations that I'm doing. So this is really important, right? Good. So let me show you what I mean, right? And this is basically now replicating the solo, but thinking about it a bit differently, right? So I'm just taking again this accounting identity. Output equals consumption plus investment. There's our production function. I'm not changing that at all, right? This is the capital dynamics, right? And if you combine these two equations now, I mean, that's basically what we did in chapter 2 too, but I'm now combining that a bit differently because I want to think about consumption next. So what we do here now is basically to say, I'm rewriting this thing in terms of investment and adding that in here, right? That's the whole idea. So then you have an equation which you can solve for consumption, move that on the left-hand side, And then you see that consumption equals production minus the capital stock tomorrow plus basically the capital stock today, right? Minus what's depreciated, right? And this will kind of be the crucial equation now, right? This is just the same one, I'm just replicating that, right? Because you can interpret this here as a constraint on your economy, right? Note that what I'm using is really just in a way, we call this, the resource constraint is basically a bit given by nature, these two equations, right? I mean, the first one is just accounting, right? Output equals consumption plus investment, right? For that you just need national accounts, right? For that you don't need any model or whatever, it's just like that what it is, right? And the capital dynamics, again, this is a bit also given by nature, right? In a way you could think about maybe you want to model this depreciation differently, whatever, but that this is kind of the process which is underlying capital, I think that makes a lot of sense, right? So in a way, for these two things, you don't have to make very strong, you're making strong assumptions here, right? I'm not saying that, but to me, these two things sound rather natural, right? So this is not related at all to behavior, maybe to say it that way, right? So this is more technology, right? Resource constraints. The interesting part is now, what does it now mean for the C, right? Where do we get C from? And that's kind of where, like, to me, the interesting part comes in, right? Because C now, we want to microphone that, we're going to get that from the household side. Right? Good. Maybe to give you some more interpretation of this equation, right? What it means. So think about this here as C is the share of production. Consumption is the share of production that you're eating, right? I mean, this is consumption. This is the share of production that you're eating. So what you're eating is your production minus the capital stock that you want to have left tomorrow, plus the capital stock that's remaining from today that you're not eating, right? I mean, a different way to think about this, you can also eat your capital stock, right? I mean, this is always one idea of these models, right? This is just one good, right? I mean, you can eat production, you can eat your capital, right? This is all just whatever, right? This is one good economy, right? So this is possible here, right? This is actually important too. Okay, so now maybe just to show you these dynamics once more, right? Why is that a dynamic constraint, right? So now say you have a situation where you know what K0 is, right? You know that K0 is equal to whatever, K0, right? This will then determine your output in the initial period. If you know what's produced, and now you have some idea what share of that production is eaten, right, my consumption, you will determine investment and you will determine K1. Right? And then once you have K1, you can basically go back to step 1 here and then continue. Right? This is just what I gave you in the solve, right? It's exactly the steps. Okay. And you can, in principle, do this up to the infinite future. Right? But what I'm not doing anymore now, I don't want to impose just this conditional share and this S, right? This constant share of production, which is saved, right? So instead, we want to think a bit about what would households actually do, right? And that's maybe just use this equation as the last thing for today, right? To think about what we call myopic households. Have you ever heard this term? Yeah?
Yeah, from your appearance, I might assume that you might be myopic yourself, because myopia is the term for short-sightedness.
Yeah, that's right. So here we're thinking about...
so basically people that want to have fun today and don't care about tomorrow.
Exactly, right? So a myopic person is what you would say, I'm not caring about tomorrow, right? So if you're a myopic person, right? Here you actually have it on the slide, right? How would you say you have a certain K0, right? You have a capital stock, your firms are taking that capital stock, they are producing something. How would you set C? What would you do?
Consume as much as possible.
Exactly, right? So you basically say, I don't care about tomorrow, right? So what I do is I eat all that's produced, and the I set this guy here to 0, right? kt plus 1, I don't care what tomorrow, right? So I don't care if there's any production tomorrow. So what I would do, I would set this thing here to 0, right? And this would mean that my consumption would equal my production plus my capital stock, right? This is kind of the thing I do. You can eat your capital stock, right? If you're a completely myopic person, we just eat the complete consumption, the complete production plus the capital stock, right? So this is the maximum consumption today. What happens tomorrow then?
Yeah, you don't have a capital stock and no function of a kt is 0, so you have 0.
So tomorrow, right, there's no production left then, right? So if you're kt plus 1, right, so this implies that kt plus 1 equals 0, right? This is just what I put here. So this implies that your output tomorrow will be 0 too, right? There's no capital, you cannot produce anymore. What does that mean for consumption? 0, right? So, I mean, that's a bit like bad luck, but that was the whole idea of this myopic household, right? He or she was just eating everything in this 0 period, right? And I mean, this is now true for all future periods, right?
Yeah, I'm a bit confused by the delta, because in period 0, there should not be any depreciation by definition, right?
Yeah, it depends a bit on the timing, right? I mean, here kind of the idea is it's depreciating at the beginning of the period, right? So you cannot eat it. You could also change the timing again, yeah, but it's really the question is when does it depreciate? It depreciates at the beginning of the period. Right? So I mean, just like but why I start with this example, right? Is that realistic? I mean, that's the question, right? Do people behave that way? And typically we would say, maybe people are stupid, but maybe not that stupid. I don't know, right? And this is exactly why we typically have this idea that people care about today and they also care about the future, right? And this is why we do these intertemporal optimizations where we're not just thinking about period 0, right? You're just maximizing utility in 0. That's the myopic guy that I just showed you. But why we will be maximizing utility also in the future, and then like extremes, right? So we take it up to the infinite future. But that's what I'll show you next week. Thank you, and then
Wird aber weitergecheckt. Ich habe den ersten eingeschaltet bei mir, so 2-3 Jahre.
Okay.